Hello and welcome to another problem from the problem 12 or from the chapter 12 homework. A uniform boom shown to the right or shown below weighs 2,950 newtons. It is supported by the horizontal guy wire and by the hinge support at point A. What are the forces on the boom due to the wire and due to the support A? So I am going to be a little more methodical about this than I was about the previous problem. Just setting up knowns and unknowns as you probably should for all given problems like this or all given problems that you have known. But first thing first, I want to show we have this very simplified version of our graph, and I have the three forces that aren't from the hinge acting on it. So I have the weight of the boom, which is what acting on it at the midpoint, at the center of mass of the boom and pointing down. I have the weight of the weight, which is the tension in the wire caused by the weight. So that's WW. That's also pointing down. And I have the tension of the other wire pointing to the left. So basically there are two wires that are pulling on this object, or there are essentially two wires because they're going to have different tensions. And one of them has the tension T. The other one has this tension which is equal to the weight of the weight because the weight is not moving up or down. Therefore, the tension that's pulling up on it must be equal to the tension that's pulling down on, or the force that's pulling it down on it from gravity. With this known, we notice that we only have forces acting down and to the left. So the force on the hinge has to be pointing up with some force, I'll call it H, in the Y direction, and another force H in the X direction, which is pointing to the right. Because we know, because this is a statics problem, sigma F is going to be equal to 0. So if there are only components in the left pointing to the left in the x direction, that means that there has to be another component pointing to the right in the x direction in order to cancel that out. And if there are only components pointing to the down in the y direction, then that means that there are going to only have to be components pointing up, and or there are going to be extra components pointing up in the y direction in order to cancel those out. Therefore, the force on the hinge is going to be pointing up and to the right, and not necessarily in the same direction as the boom. Because it's a hinge, it has a little bit of wiggle room, and it can point with whatever force is necessary in order to keep it from moving side to side or up and down or rotating or anything like that. So we know then the weight of the weight, the weight of the boom, and choosing this to be our zero, choosing the hinge to be our zero because it is the point where we know the least amount about. We don't know the HX or the HY, so we don't want that to contribute to our torque at all. We choose the hinge to be our 0 point, our pivot point, and then find the radius B is equal to the L divided by 2. Radius of weight of the weight is equal to L, and radius that it takes to get to the tension is also equal to L. So the unknowns then are going to be T, HX, and HY. So in addition to the forces that we have in the X and Y direction, which can be used for solving or the forces in the X and Y direction can be used for solving for two of these variables, but we need to solve for three of these variables. So we're going to have to also include the fact that as a stacks problem, torque is equal to zero, which we already kind of did when we were setting up our knowns and unknowns. We brought up the length or the distance between our hinge and each of these points was L over 2 or L or L. So force X equals 0 and force Y equals 0 are going to give us the fact that this is going to be Hx minus tension, the sum of all forces in X. Therefore, Hx has to be equal to the force of tension. The sum of all forces on Y state that Hy minus weight B minus weight of the weight uh, is equal to 0. Therefore, Hy is going to be equal to the weight B minus the weight of the weight, plus the weight of the weight, rather. So we've already solved for one of our three unknowns just without doing any sort of algebra whatsoever. We just set up the fact that the Fy has to be equal to each other, and that gave us the force of H in the Y direction. But what is H in the X direction and what is T? In order to do that, we have to find the sum of all of the torques, which is going to be equal to uh, where each torque is equal to R cross B is equal to R perpendicular, or R, not R cross B, sorry, R cross F is equal to R perpendicular times the force, or alternatively is equal to R times the force that's perpendicular to R. So R perpendicular is going to be a little ungainly when it comes to drawing these out. So I'm going to find the force that's perpendicular to R. That means finding the force that is in the direction perpendicular to R. So in this case, we find that if this is theta and this is 90 degrees, as is going to be the case because the gravity is going to always make an angle of 90 degrees with respect to the ground, unless you're on a ramp or something like that, then this is going to be 90 degrees minus theta, meaning this is theta. Therefore, F perpendicular is equal to weight B cosine of theta. That's also going to be the case over here because they're pointing in the same direction. So F perpendicular here is also going to be weight of the weight cosine of theta. But for the tension, you find that this is 90 degrees minus theta because it's a similar angle to the smaller angle that we did earlier. Therefore, this is theta. Therefore, this F perpendicular, the portion of the F that's perpendicular to R, like we were finding earlier, is going to be equal to T sine theta. So that sets up a lot of our forces. That sets up a lot of our torques, but it is a little hard to set up still because we need to know which ones are going to be positive torques and which ones are going to be negative torques. And the way you can do that is one by using the right hand rule, pointing your finger along the direction of R, pointing your second finger down on the direction of weight would put a force that or a torque that's into the screen, which is a zero torque. Alternatively, if you look at the tension and then put R this way, R pointing up, and tension pointing to the side, that's going to give you a force coming out of the board, which is going to give you a positive torque. So you can do the right hand rule in order to solve for what the torque is going to be. You can also just understand intuitively if you pull something that's to if you pull something to the right down, it's going to cause there to be a counterclockwise rotation. So those two weights are going to cause a counterclockwise rotation, which is a negative torque. And that tension, which is pulling something to the side, uh, to the right, to the side, is going to cause there to be a positive torque. So either way that you want to do that, that's fine. So sum of torques is equal to 0 hx plus 0 hy times sine or cosine. I'm not going to 0 cross h, let's just say 0 cross hx and 0 cross hy. I'm not going to go through how to find the sines and cosines there because they're not really important right at the moment. Minus plus minus L over 2 times weight B cosine theta minus L times weight of the weight cosine theta plus tension times L times tension sine of theta, which is going to be equal to 0. So L tension sine theta is equal to L over 2 weight B cosine theta minus L weight cosine theta. So tension is going to be equal to weight of the beam divided by 2 tangent of theta plus weight of the weight divided by tangent of theta. And then for this example, the angle is 45 degrees, so all those tangent of thetas are going to equal 0, so it's just going to be weight of the beam divided by 2 plus weight of the weight divided weight of the weight. So this is solved for in terms of your unknowns. You can then use that to solve for this and use the fact that h, the magnitude of h, is equal to the square root of hy squared plus hb squared or hx squared to solve for the magnitude of h, which is what it asked for in the second part of the problem. Okay, I probably should have led with this. This one was a little bit more complicated, but it also did give us a lot of chance to play around with different torques. But if you have any more questions, then please feel free to reach out to me and I'll see you again later.